Hello students, so now you have completed exercise 9.1, which was based on which parallelogram will lie under the same base and between same two parallel lines. Now from here two theorems are important, or two conclusions we can say that, which are important, and those are: first one is, if two or more parallelograms lie on the same base and between same two parallel lines, then the area of all the parallelograms lying under those criteria will be same. Suppose if I draw a parallelogram, this is A, B, C, D, right? And if I draw another parallelogram, EFBA, and if I draw another parallelogram, say this one, or name this is G, this is H. So all these three parallelograms, these are lying on the same base, that is AB, and between same parallel lines, say line L and line M, right? Line L, line M. LM and L and M are the two parallel lines, and AB is the common base on which all these three parallelograms are lying. So what my point is, the area of in the given figure, in this figure, what we will first do is, here you can clearly see that two parallelograms are drawn, and those are ABCD and EFCD. These two parallelograms are lying on the base DC and between same two parallels, that is AF and DC. Now look at these two triangles which are formed here. One is triangle AED and another one is triangle BFC. So triangle AED and will be equals to angle B. Why? As line AD and line BC, these are two parallel lines which are intersected by a transversal. Then their corresponding angles, this and this, which means angle A and angle B, are equal, right? So let me write it again. Triangle AED and triangle BFC, these two triangles, first one is angle A is equals to angle B, as AD and BC are two parallel lines which are intersected by transversal AB. Now again, DE and CF are two parallel lines which are intersected by transversal AF. So angle E will be equals to angle F, right? So automatically, if these two angles of triangle AED are equal to angle B and F of triangle BFC, so angle D will be equal to angle C. How? You add angle A and angle E and subtract their sum from that 180, you will get angle D, which is same as the difference between 180 and sum of B and F. So angle D and angle C will be equal. Now next thing is, if ABCD is a parallelogram, then AD, these two triangles, triangle 1 and triangle 2. These two triangles are congruent. Now, considering the parallelogram ABCD, the area of this parallelogram ABCD can be written as area of triangle AED plus area of quadrilateral BECF plus area of quadrilateral BEDC or EBCD, right? This and this, the sum of area of 1 and 2 will give us the area of parallelogram. Now, as we proved that triangle AED is congruent to triangle PFC, so their areas will also be equal, right? So I can replace area AED with BFC. So I'm replacing area of triangle AED with area of triangle BFC. So BFC plus this quadrilateral again EBCD. If you add these two figures, that means second and third one, what you will get is you will get your parallelogram, that is EFCD. So the area of parallelogram ABCD became equal to area of parallelogram EFCD. This was a simple proof. Now let's move on to the questions related to these. Now in this question we are given that ABCD is a parallelogram. We have to prove that area of ABCD is equals to area of that rectangle. Area of parallelogram is equals to area of rectangle. Now as we know that rectangle is also kind of parallelogram, and this rectangle and parallelogram both are lying on the same base and between same two parallels. So by using theorem 9.1 we can say that the area of these two parallelograms will be equal. Now area of ABCD, because if we suppose that area of rectangle EFCD will be DC into ED, area of rectangle EFCD will be equals to DC into ED, and ED is equals to LA and DC will be equals to DC only. So area of ABCD will become equal to area of that rectangle. Now another important conclusion is that if triangle and a parallelogram are lying on the same base and between same two parallels, then the area of that triangle will be half of the area of parallelogram. So let us talk about this figure. What we have to prove is we have to show that area of triangle PAB will be half of area of ABCD, right? We wish to prove this. So here we have triangle PAB and we have parallelogram ABCD. Now what we will do is we will draw a line which is parallel to PA from B. So this is our parallel line, right, which is parallel to PA. Now we can see here we have two parallelograms, that are ABCD and ABQP. So these two parallelograms will be equal in area, and also PB is the diagonal of the parallelogram ABQP, which will divide this parallelogram into two congruent triangles of equal area. So area of triangle ABP will be equals to area of triangle QPB. These two triangles will be equal in area, and also we have seen that the area of parallelogram ABCD is equals to area of parallelogram ABQP. So we can write area of parallelogram ABCD is equals to ABQP. ABP plus QPB, right? Now we can also say that area of parallelogram ABCD will be equals to twice of area of triangle ABP, right? And dividing 2 on both sides, what you will get is half of ABCD is equals to ABP. This is the thing that we wanted to prove, that if a triangle and a parallelogram lie on the same base and between same two parallels, then the area of triangle, that is area of triangle ABP, will be half of area of parallelogram ABCD. Right, so this was again a easy proof. Exercise 9.2 is completely based on the above two phenomena, or the other two above two theorems. So try exercise 9.2, and in the next video we will be discussing about what happens if two triangles lie on the same base and between same two parallels.